Hello everyone, welcome to a new video by Avishub, your SAT and AP content creator. So today we're going to be talking and covering the Calc BC review. So are you self-studying for AP BC, AP Calc BC, but you can't find the right concise course for it, you're short on time, but you still want to get a 5? Well, then welcome to the Calc BC review by Avishub. Of course, this covers the AP uh, AP Calc AB course as well. So let's talk about some prerequisites. If you haven't done basic pre-calc, like the curriculum that is in AP pre-calc, like algebra, trigonometry, geometry, polar curves, and everything else that's there, you need to cover that first. If you've done it in school, then that's okay. You can jump right into this video. But if you haven't, and you can just go to Khan Academy, binge watch all the videos, do questions, and just, try to familiarize yourself with all these questions and these concepts because they are vital in AP Calc BC. So let's begin with the first chapter, that's limits and continuity. So the portion for this chapter is 4 to 7%, and I am not gonna tell you the theoretical definition of a limit because instead of telling you about what it is in words, I'm gonna show you what it is. So let's talk about a function. So I have a function here that is x plus 4 upon x minus 4. The graph of f of x looks somewhat like this with a vertical asymptote at x is equal to 4. And okay, to describe what an asymptote is, we need to know what a limit is. So let's just say that there is something called as an asymptote. Okay, so there's an asymptote at x equals to 4, but we're not going to talk about it right now. First, let's take a point on the x-axis. Let's take a point on the graph. Let's take x is equal to 8. So if you put 8 in f of x, we'll of course get 3. But if you couldn't, let's say, input 8 into f of x and you needed to approximate it using different values, using any values on the left hand side of x is equal to 8 or right hand side on x is equal to 8. So what you can do is you can make a table. You can say that, okay, I'm going to input 7.9. So your 7.9 is going to be somewhere around here. 7.99 and 7.999, and you're basically going closer and closer to 8. This is going to be a very minor difference, and when you input all these values, when you calculate, your f of x will also come closer to the actual value, which is 3. So it's at 7.9, it's 3.0512. At 7.99, it's 3.00501. At 7.999, it's 3 point triple o five double o one. So your value is getting smaller and smaller. It's getting closer to 3, but it's never exactly 3. It's only getting closer to 3. As you can see, when you're approaching from the left-hand side limit, when you're approaching from, let's say you're talking about at x is equal to 8. So when you're going from any value that's less than 8, and you're increasing it till as you get closer and closer to it, you're talking about the left hand side limit. Okay, like on a number line, let's say you have 1, and at the left hand side you have numbers like 0, -1, -2 till negative infinity. On the right hand side you have numbers like 2, 3, positive infinity. So when we are talking about the left hand side, you're basically approaching from smaller numbers and we are scaling them up. To the number that we want. In this case, we're talking about 8. So we take a small number that's very close to it, 7.9. We increase it and we get closer and closer to 8 as 7.99, 7.999. And our f of x also gets closer and closer. If we were to do this on the right hand side, let's say 8.01 and then 8.001. And as we get closer and as we make our numbers smaller and smaller, from a larger number to a smaller number to get closer to our x, our f of x will also become f of x will increase and it will come closer and closer to the actual value, which is 3 in this case. This is called as a right-hand side limit. As you see, your values, they become more and more closer coming to the actual value when approaching from the left-hand side and the right-hand side limit. This is what limits is all about. Limits is not talking about the actual value at which the function exists at, or at which the function is continuous. Just for right now, just believe that continuous is it means something, but basically limits is all about approximating the value of that function at a point by approaching from both sides, and both of these sides, they all like converge to a single number, they come closer to a single number, and that is your limit. So it's like an indirect way of calculating a function. Right. So yeah, well, for a limit to exist is something, for a limit to exist in several functions, as you will see, there are going to be functions such as this, as you, yeah. So when, let's say you're talking about x is equal to a here, this is your f of x and this is a. So when your limit is approaching a or f of x, when you go from your left hand side, you will see that your numbers approach this number on the y-axis. But when you're coming from the right-hand side, instead of that, you get a other y value, and these two y values are not equal. So in this case, we say that the limit does not exist. So when you approach from the left-hand side, your x, the notation to say is limit of f of x as x tends to 8. That's what you're going to say. In this case, since there's a minus, you say 8 minus, and f of limit f of x extends to 8 plus. Or you can also call it 8 minus is the left hand side limit and 8 plus is the right hand side limit. So for a limit to exist, you need for the left hand side limit to be equal to the right hand side limit. As in this case, both of these limits are approaching 3. Therefore, these two limits are going to be equal, and thus limit f of x as x tends to 8 is equal to 3, and it exists. So that is your basic limit. Now let's talk about the asymptote here. So what about at x is equal to 4? We're taking the same, this is the same graph of f of x. Right here at x is equal to 4, we see that the left hand side limit, first it intersects the x-axis at -4, and then it goes down towards infinity. We observe it goes down towards infinity, and it becomes closer to x is equal to 4, but it never really matches x is equal to 4. It's always getting closer, but it's still not there. So if imagine this is x is equal to 4, this yellow line is x is equal to 4, and the purple is the left-hand side limit of f of x. So this will get closer and closer and closer and closer, but there'll always be some distance between them. So these two values are never going to be equal. They're only going to get closer and closer until your y becomes negative infinity. It's going to go forever and ever, but it's never going to equal it. So you can say that it approaches negative infinity. When you're talking about the right hand side, you can see that it goes to y positive infinity, and the same thing happens. So if this is x is equal to 4, and this is the right hand side limit of this is the right hand side of the graph, you will see that this graph also is closer and closer and closer, but it never quite matches x is equal to 4. The value is never equal to that. So that's why we say that the right hand side approaches positive infinity, while the left hand side approaches negative infinity. And in this case, since negative infinity is not equal to positive infinity, the limit is said to not exist. This right here, this line where a function does not exist is called an asymptote. If you're wondering why it doesn't exist, if you were to look at f of equals f of x, you will see that at x equals 4, right here, your denominator equals 0. This f of x equals 8 upon 0. And this is an intermediate form. Okay, basically it's not, this violates the rules of math. 8 upon 0 like yields nothing. It's invalid. So we come across an asymptote at that point. The graph does not exist. It simply approaches infinity, since theoretically 8 upon 0 is supposed to be equal to infinity. But when you graphically try to represent it, the graph basically goes on till infinity, but it never actually reaches infinity, nor does it reach a constant value. So that's the basics of limits. Now let's talk about actually solving these questions. So here are some algebraic properties. So if we were to calculate, let's say, limit x tends to 3 of 3x squared. So you can take, as 3 is a constant value, you can take it out of the limit function, and you can rewrite this as 3 times limit x squared as x tends to 3. And you can simply input whatever number x is tending to in the equation to get the answer. Here is the algebraic notation with all the constant values. For you can also, if you do not understand the example well enough, you can always see this. Yeah. Moving forward, and this is, I'd like to call it a distributive property. Let's say a limit is applying to, let's say, x squared plus x cube. So you can multiply the limit to x squared, and you can then add it to multiplying the limit to x cube, as in this form. And then you can input the limits as usual and get your answer. Here it's written. And the other one is when you're let's say two functions of x are being multiplied together, and a limit is on the entire function, then you can multiply the limit with each single function and then multiply it whole throughout to get the answer, as you can see right here. And this is the constant notation for it. Okay, so let's come on some problem solving. So let's talk about algebraic manipulation. So if we have a function here, we have its limit of x square minus 7x minus 30 upon x square minus 12x plus 20 as x tends to 10. If you were to plug in x is equal to 10, you would get 0 upon 0. So how are you meant to solve this? Well, since this is a quadratic equation, first thing you need to do is try to separate it into factors. Now you obviously use the quadratic formula, which is minus b square minus 4ac upon 2a, and you can get the factors of both of the quadratic equations, and you would find that x minus 10 is common for both the polynomials. So you can divide by x minus 10, you could cross them out, and then you can input 10 as x, and you would get the answer as 13 by 8. So that is one way. Polynomials divide by polynomials. This is strictly for as x approaches infinity or negative infinity, positive or negative infinity. So right here in this question, 8x squared minus 4x plus 1 upon 16x squared plus 7x minus 2. If you were to input x equals infinity in this, you would get infinity by infinity, which is invalid again. 0 by 0 and infinity by infinity, all of these are indeterminate forms. So how are we going to solve this? Well, when you're solving polynomials divided by some other polynomials as x approaches positive or negative infinity, you divide both the polynomials in the numerator and in the denominator by the highest power of x in the entire function. So right now the highest power of x is x squared. So we'll divide both the polynomials by x squared, and we'll get 8 minus 4 upon x plus 1 upon x squared upon 16 plus 7 by x minus 2 upon x squared. Now when we input x is equal to infinity, 4 by x will become 0, 1 by x squared will become 0, 7 by x will become 0, and 2 by x squared will become 0. And therefore the remaining part would become 8 by 16, which is equal to 1 by 2. Here's a tip for you to do this to save time. This is only for your time efficiency, and this will definitely help you in multi MCQs. So if there's a limit as x tends to plus minus infinity, and let's say you have two polynomials, you have two functions of x, let's say f of x and g of x. So if your f of x has a higher power than g of x, then you would instantly get plus minus depends on whatever x is tending to plus minus infinity. If your g of x is greater than f of x, then you would get something like 1 upon infinity, you would get 0. And if they are equal, then you would simply get the coefficients of the highest power. For example, in this equation that we did, in this example that we did, the highest power, yeah, the highest power of the coefficient of the highest power of x were 8 and 16. And in the end, your answer was 8 upon 16 or 1 by 2. So this is a tip and it works every time. There are no exception cases to this. If you see two polynomials, right, and they have the same degree of x, same power of x, then you can simply like take the fraction of the coefficients of the highest power of x and solve them to get your answer. That's the short way to do it. And on MCQs where you don't have to show any sort of working, it's really useful. So yeah, x tends to infinity, g of x has a higher power than it should be f of x right here, has a higher power than f of x when it yields 0. If both of them have the same power, highest power, then the constant or the coefficient associated with the highest power is left behind. So let's say that's a sub n upon b sub n. Okay, so that's it for limits. And there are some other sorts that we'll do after doing continuity. So it's in the session only, so you don't need to panic. Okay, so first talking about continuity, let's talk about the opposite or anti version of it. That's discontinuity. So there are three types of discontinuity, and the first one is jump discontinuity. So let's say you have a graph such as this. Let's say you have f of x here, and at x is equal to a, when you approach from the left-hand side, you see that your number at y is this. And when you approach from, let's say this is y is equal to b, this is b, and you're approaching from the right hand side, your number converges to something, let's say y is equal to c. And it's very clear that b is not equal to c. Therefore, uh, the limit does not exist at x is equal to a. But what's more important is that the you could say that the graph is discontinuous at x is equal to a. Which, yeah, as you can see right here, that at x is equal to a, the graph existed here and then it jumped to a new value. Let's say b and c. Yeah. So at x is equal to a, like just before a, the value for the limit was y is equal to b. But just after a, the value jumped suddenly to y is equal to c. And that's why it's called a jump discontinuity. Your y, output you get by inputting x is equal to a, it changes as your limit shifts from left hand side to right hand side. It jumps to another value. And basically, if you see a graph break, like there's a break, there are two values that correspond. Therefore, there is a jump discontinuity present there. It's not that complicated. It's very easy to understand. Okay, essential discontinuity. Essential, we encountered essential discontinuity before, and essential discontinuity is basically an asymptote. In the first question, when we encountered x plus 4 upon x minus 4, we had an essential discontinuity or an asymptote at x is equal to 4 because the function could not exist there. That is your essential discontinuity. And you will also encounter how to remove this, and we have done it before in this question right here. So I'm just gonna, yeah. So let's say that you have x plus 2 times x minus 10 upon x plus 3 x minus 10. This is your f of x upon g of x. Well, and no, wait, this is your f of x. Yeah, so your f of x does not exist at 10 because then your denominator would become 0 and Therefore, there's an discontinuity there. But if you factor it out, the quadratics in this form, then you can just cross out x minus 10 and suddenly it exists at x is equal to 10. This is called removing an essential discontinuity, and you can encounter questions about removing this discontinuity in some function of x in the AP exam. So yeah. Anyways, moving on, we have something called as a removable discontinuity. Removable discontinuity is basically the act of removing this. Removable discontinuity, you can call it removing an essential discontinuity, is something, an essential discontinuity that can be removed is called a removable discontinuity. Yeah. Anyways, moving forward to the next part, defining continuity. So there are three conditions that a function should meet at some x is equal to some value for it to be considered continuous at that some value. So the first condition is, let's say that for f of x to be continuous at x is equal to c, the first condition is that f of c must exist. The second condition is that the limit as x tends to a for f of c must exist. And the condition three is that f of c as is should be equal to limit of x tends to a for f of c. Therefore, condition three is basically that your condition 1 should be equal to condition 2. These three conditions are what defines continuity. So let's jump into questions straight away. So right now here we have something called as a piecewise function. Piecewise function could sound really complicated, but it's not. It's basically a function that's represented as such, with different functions describing that function on different intervals. Like right now, f of x could look like what I don't know how f of x looks like, but at x less than 2, let's say this entire part, for you need to find a value, you need to use x plus 7. At x is equal to 2, the value is 9. It's a constant value. At x is greater than 2, you need to use 3x plus 3 to get a y value. So basically, f of x is like you can imagine it's some sort of a puzzle, and there are limits, there are different intervals like less than 2 to negative infinity, there's 2 to positive infinity, and all of these puzzles need a different variation to solve them. So that's basically functions and piecewise functions, and it's not that hard. So I'm gonna tell you how to solve these because really going in depth would just make it more complicated. So first condition is, does f of c exist? Well, we need to find at x is equal to 2. So does f of 2 exist? Yes, it does, since it's been clearly mentioned that at x is equal to 2, f of x is equal to 9. So our condition 1 is true. Condition 2 states that limit f of c exists at x tends to c. Now, how are we going to find the limit? Well, to check if the limit exists, we'll have to find out if your left-hand side limit is equal to your right-hand side limit. So here we have the left-hand side limit, and right here we have the right-hand side limit. When we solve these two questions, as we go to the left-hand side limit, we're approaching from negative infinity to 2, and not exactly 2, like 1.99999. And from the right-hand side limit, we're approaching from positive infinity to like 2.0001. And when we solve this, for the left-hand side, we are given this equation, and for the right-hand side, we are given this equation. So we input the values and we get 9 on both sides. Therefore, the limit does exist. Now, condition 3 is, does condition 1 equal to condition 2? And the answer is yes, they are both equal. Therefore, f of x is continuous at x is equal to 2. So this is your typical question on continuity for the AP exam. Now let's mix it up a bit. Let's do something different. Let's say that f of x is continuous at x is equal to 4. We know it's continuous. The question is asking what must be the value for k for this f of x to be continuous at x is equal to 4. So it's mandatory that f of x is continuous, but we need to find what value allows or what value or values allow k to be continuous at x is equal to 4. So we check for the condition 1, we input 4 in it, and we get f of 4 is equal to 0. So it does exist. It can be any value. It just needs to exist. The condition 2 is, does the limit exist? So we'll take the left-hand side limit, which is 0, as we already calculated f of 4 is equal to 0. And we'll take the right-hand side limit. We'll input 4 and we'll get the expression 16k minus 8 minus 1, 16k minus 9. Now, basically, we know that f of x is continuous. Therefore, all three conditions must be true. That means your second condition must also be true. That means LHL should be equals to RHL. This should be your order of thinking. This should, whenever you see the question, this should be in your subconscious mind. You should just, when you're solving the question, you should know that these are the series of steps, or this is the logic behind whatever your steps are. Why are we like, why are we equating LHL equals RHL? Because we know that the second condition must be true since f of x is continuous, and therefore all three conditions must be true. So we equate 16k minus 9 is equal to 0, and we get k is equal to 9 by 16. And that is your answer. Okay, so that is the end of continuity, and let's move to standard limits. So you need to memorize all of this, and I don't know if this is given in the AP exams formula sheet. I'm not sure, but if it is given, then well and good. I haven't really written the most obvious limits. Here are some trigonometric limits and some limits that are used for the JEE exam. So you can read them. I'm not gonna recite them for you. All of these are important. I have never seen these two appear or even this appear. This, this, this one, and this one. Especially these two and this one. These like limits 1 and 2, these are very important. They come, I think, every time. I have never seen a paper without these coming in the limits and continuity questions. So be sure to memorize all of them. All of them are important. Okay, so there are some, okay, we already discussed indeterminate forms. I'm going to skip over this. And this is basically the sort of algorithm or series of steps you're supposed to follow when you're calculating a limit for f of x. So your first thought should be to directly substitute your x as a, and if you get something such as b upon 0, therefore, which is an asymptote, so the graph does not exist at that point. So the limit doesn't exist. And if it gives us an actual number, then great. That means you have found the limit. Your answer is correct. Most probably it's correct. And now we're coming to the most common thing that you're going to encounter, that is an indeterminate form. So for an indeterminate form, you can do three things, which are factoring, conjugates, trigonalities, and the fourth is approximation, though I haven't really encountered any approximation questions. So I would say the majority three steps that you can use. Factoring, in which you can factor the quadratic expression or whatever expression you're given, cancel out the term that is like giving you the indeterminate form and get your answer. Conjugates, we are gonna do some questions on conjugates, and the other is using trig identities. That is all of this. That's why these are so important, because this is like an entire one third of all indeterminate form questions for standard limits on the SAT, not SAT, AP Calc. Okay, so here are some easy question drills. This does not contain conjugate questions. We're going to do them later on. So just go through all of this, pause the video, do all of these questions on your own. I'm going to show you the solutions just in a minute. So wait, yeah. So these are all the questions, as you can see. I'm going to give you like 5 seconds, just pause the video. Okay, so I hope you're done now. And let's move on to the solutions. So for the first question, you're basically gonna input the limit, we get the answer 9. If you got 9, correct, well and good. In the second one, we're going to do the same. We get 0 as the numerator, and therefore your answer is 0. I hope you got that correct as well. These are all easy questions. In the third form, when we input x is equal to 7, we get 0 upon 0. That's an indeterminate form. So we'll factor the quadratic equations, we'll cancel out the x minus 7 term, and we'll get 11 by 9. In the fourth question, we are given a limit as x tends to infinity, and here the coefficient of the highest powers are 4 and 5. So you can divide both f of x and g of x by x cube and solve it the long way. I've written the answer directly, which is 4 upon 5. Next, we have got a trigonometric limit, and this is your, if you couldn't answer this question, then yeah, this is important to focus on this one a bit. So, as limit x tends to 0, f of x is equal to 4 sine 3x upon 2 tan 5x. This is equal to 2. Yeah. So the first thing we're going to do is multiply limits to the numerator as well as the denominator. Limit x tends to 0 sine 3x upon limit x tends to 0 tan 5x. Now, if you remember, limit x tends to 0 for sine uh, ax by a should leave you with 1. Or if we see it, yeah. And this is the same for tan. So for tan ax by ax is equal to 1. So we're going to divide this by 3x and multiply this by 3x. And we're going to do the same for tan. We're going to multiply and divide by 5x. So we're going to cancel out the x term. We're going to take 3 by 5 outside the limits. We'll get 6 by 5. And limit x tends to 0 of sine 3x by 3x is equal to 1. So this equals 1. And limit x tends to 0 for tan phi x by phi x is equal to 1. So it becomes 2 times 3 by 5 times 1, which is 6 by 5. And that is your answer. Sixth question, limit x tends to phi 11 upon x squared minus 25. When you input the value, you'll get 11 upon 0, and therefore the limit doesn't exist. So let's check the left-hand side limit and the right-hand side limit. And if we check, we'll basically, at this point, you will get some number that is like 25.000000 till minus 25. So it will be 11 upon 0.000 till some infinity. There's some one is there, and this is basically the positive infinity. For this one, it will become 24.9 minus 24.9999 till infinity minus 25, which is 11 by negative 0.00001, which is negative infinity. And since these both are not equal, therefore your limit does not exist. So that's all for limits and continuity. I am going to be adding the conjugate part. I'm going to record it right now. So yeah, see you in that video.